Hey guys, time for some grad school rep. So recently I was doing some reading on the topic of GPU programming, especially code optimizations for CUDA programs, and I came across this really interesting paper called RedSan. Uh, it's written by Yanbo Chow. He's the primary author. I believe he's a PhD student at NC State, where I graduated from last year. And one of the co-authors is Professor Jaja Lee, under whom I had the opportunity to take a course of parallel computing. So that kind of motivated me to make a video on this paper, and it's actually a very good read. And I've attached the link here if you guys want to go and check it out for yourself. So this paper introduces a software tool called RedSan. It's essentially a sanitizer or kind of like a profiler to help you find redundant, unnecessary memory instructions in your CUDA programs. The other thing that this paper contributes is it finds an implication in CUDA keyword called restrict, and it tells you how the usage of this keyword can lead to some implications, and that was like the more interesting aspect of this paper for me. So before we get into the details of this paper, let's look at one thing, and that is why GPU optimization is harder than it looks. Okay, there are three reasons. The first one is pretty obvious. We all know that GPUs are massively parallel, so it has thousands of threads working together in lockstep, and how these threads work together, that's where the hotspots in your code emerge from. Hotspots are basically inefficiencies or where your code essentially lacks, and so it's not single thread dependent. The second reason is the memory hierarchy of GPUs. As you guys might know, the GPU memory system is pretty complex. It has a bunch of different memory options that you can use, like registers, shared memory, L1 L2 cache, and global memory. And one wrong access pattern can kill the throughput of your program heavily. The third reason is the compiler toolchain. The NVCC is kind of like a black box. You don't really control it, or you don't really see what's happening behind the compilation process. So all these things make it hard to optimize CUDA programs. And the existing profilers like NVIDIA's Insight Compute or Compute Sanitizer, they might tell you something like the function A is 70% efficient, or the function B is taking 80% of your memory, but they won't exactly tell you where in your source code the inefficiencies are coming from. They won't be able to link the inefficiencies back to the source code, and that's where this paper comes in handy. So before we look at how this red sand tool works and how you can use it, let's first look at how we can build optimized binaries from CUDA programs. So your compiler is capable of optimizing the code for you. It can do some things automatically to make your code more optimized. For example, it can unroll your loops. It can check where you don't really need a loop and remove that. It can remove any dead code from your program. It can also convert some memory accesses to register allocations. It can do some vectorization if it is compatible with your program. It can do some other things. So that's what building an optimized CUDA binary means. So for to do that, if you use a compiler like NVCC, you just use this command, like nvcc dash o3 dash line info dash architecture sm89. So this architecture depends on your GPU hardware that you are using. SM89 works for, I guess, RTX 4090 or something, and for some different GPU hardware, you might have to change this flag. This flag line info dash line info basically creates a mapping from your assembly code to your source code, CUDA code, that helps profiling it with Insight Compute. And the most important flag is dash o3, that tells the compiler to optimize this program to its maximum efficiency as much as it can, and give you the best version it can produce. And whenever you are producing code for production, you have to use this flag. And then we are just mentioning the CUDA file name and the output file name. Now, once you have got the optimized binary, you might think that's it, right? That's the best you can do. If it is already optimized by the compiler, it might be the most efficient version. But that's where this paper comes in. The authors talk about four scenarios because of which even the optimized CUDA binaries have some inefficiencies left behind. So let's look at that. So these are the four patterns the authors talk about. The first is called duplicated access. So let's get into the first one before we talk about the others. So if you look at this code, it's an excerpt from the paper, and this is a CUDA kernel, basically a CUDA function. In this function, you might see there is a for loop. This function takes a pointer to an input array and a pointer to an output array. And what is essentially happening, every thread on your GPU will receive this function. Every thread will calculate one in index, which that thread will use to get some uh, value from this input array, and then that value will be added to this out index inside the output array. But as you might notice, this out index never changes inside this for loop, right? Because this out index is set before this for loop even begins. It never changes inside this for loop, and that's what we call as a loop invariant. It's an element that never changes inside your loop. And because we are doing a memory access to this index that never changes, we are essentially doing a redundant access, because every time this instruction hits, you have to load this value from this memory, from this output array, then you add the input value to it, and then you store it again. So every time we are doing essentially two redundant accesses, one to load that value and one to store it. And why is it bad to do a memory access here to the output array using this out index, which is a loop invariant? Because this output array is probably stored in global memory. Because most of the times arrays might be very large in size, they might be stored in global memory like your RAM or like the GPU memory, VRAM. So it's not the fastest. Doing an access to VRAM is the slowest access you can do. Instead of that, if you were able to store it to a register, which is like a temporary variable that you will use, like in temp, that will be stored on the register closest to your thread, closest to your compute unit, and that will be the fastest memory access. That's why we want to avoid this memory access. So let's say the programmer forgot to do that, but your compiler is able to optimize your code and do that for you. Your compiler is kind of built to do that for you, but in this case it won't do it. And that's the first reason even the optimized binaries get some inefficiencies, because we are using two pointers here. Your compiler plays it safe and thinks that what if these two pointers point to the same memory address at some point. So because of that, it will never cache this value of out index into a register. It might always think that this value might be updated at any point, maybe by some different pointer, but so we won't cache it. It might be updated, and that's what prevents from this code being optimized. And how we can loop around it, or how we can fix it, is this keyword called restrict that CUDA provides. If you add this keyword before this pointer name, like in float star restrict input and float star restrict output, it essentially tells the compiler that these two pointers will never point to the same address. So if there is a possibility or a chance for optimizations, like converting or storing it into a register value, then do that. And that's how this keyword helps you get rid of this inefficiency. But there is an implication with the usage of this restrict keyword that the authors found out, which was not documented in the CUDA documentations. And let's look at that. So when you use this restrict keyword, the compiler happily caches that data to a register if it finds an opportunity to do so, assuming that this location, this memory address, will not be pointed to by any other pointer. But it doesn't know that this keyword only guarantees no aliasing within a single thread. So only uh, other pointers from this single thread won't be able to point to this data, but given that GPUs have so many number of threads working together, there is a possibility that some other thread can point to this memory address and even update it. And if something like that happens, and if you a compiler has already decided to cache that data to a register, your current thread that holds this restricted data will not be able to get that updated data. And that's one of the implications of using this keyword, that you might get some stale data if some other thread updates this, because this restrict keyword doesn't guarantee aliasing across multiple threads. So the simple analogy would be like if you check the weather app once in the morning and it tells you that it's going to be sunny all day, and then you trust that forecast, you keep the phone inside and you never check the weather app again, and you go out at night and there is a storm, right? It's something like that, that your compiler has cached a value to a register and hoping or thinking that given this is a restricted uh, pointer, no other pointer will point to this exact memory address, but some other thread is pointing to it. So that's the implication that we need to be careful about. Now let's look at the second scenario because of which inefficiencies get through the compile phase into your optimized binaries, and it's called loop invariants stuck inside if branches. So we already looked at what loop invariants are. Now if those invariants are inside conditional statements inside your for loops or your loops in general, then that gets even worse for your compiler, because if this conditional statement inside the loop is input dependent, it won't be able to guess if there is this block will be executed, and if there is a redundant memory access inside this block, it won't be able to optimize for it. So that's like a pretty simple straightforward reason. And even if you use a restrict keyword or a pointer which was defined as restrict keyword inside this if block, compiler doesn't know about it, compiler doesn't care about it, so it won't be able to optimize it. Very simple. And the third and fourth scenario because of which inefficiencies get through your compile phase are related to your algorithm design, more or less. Third reason is like outdated features or outdated algorithms. As GPU hardware evolves at rapid pace every year, we also need to evolve our software design techniques, or especially for GPU programming. One instance is using volatile shared memory plus sync threads to share data between threads, which is an old way. And given the new GPU hardware that has been around for a while, some modern way is some features like warp shuffling, which basically gives access to different threads registered directly without using any shared memory. So you can directly get access to other threads data. And the fourth reason is inefficient design. If you like basically make a design of your software which is false, or which is like inefficiently designed, like using shared memory for values only one thread is ever going to use, that's just a bad design from the programmer, and the compiler can't do anything about it. So these are the four scenarios because of which compilers kind of can't do everything for you. On, let's look at the actual red sand tool introduced by this paper and how it works. So it starts with taking your optimized CUDA binary, then it applies some CUDA binary filters, it does some NV-bit instrumentation, and after that, after the runtime, it does some analysis to generate a CSV report for you. So what it is essentially doing is during the runtime, it takes note of every memory access that your program makes, and it just logs it. It just logs it into some data structure, and that data structure is every log of a memory access holds which program counter or which line in your program made that access, which thread was used to make that memory access, and was if it was a load memory access or if it was a store memory access. And after this data has been collected during the runtime, it runs some analysis to to tell if a certain line in your program where the memory access happened from was redundant or was not redundant. So how does it decide if it was redundant? It gives us three rules. The first rule is called dead store. So if the same thread makes an access to a memory location to store a value, and then in the next instance it again does the same access to store a value without that value actually changing, then that is considered as a dead store. The second is dead load. It's the same concept, same thread, same address, and a load after a load, then that's called a dead load. And the third is load after a store. Again, it makes sense, right? If you just stored a value at a memory location, and then in the next instance, if that value hasn't changed and you load that value from that memory address, it makes no sense. You could have just loaded it from your local register that you previously had that value at, right? And depending upon how many times a redundant memory access happens from a program counter in your program, it puts that line or that specific instruction into one of these four buckets. It decides if it's fully redundant or partially or slightly or non-redundant. So yeah, that's how it collects the data for you. Now, before taking a look at RedSan in action, looking at how it actually works and how we can use it, let's look at how we can get a baseline benchmark for your CUDA program with Insight Compute, which is NVIDIA's own profiler. So for that, as usual, you would compile your program first with NVCC using compile optimization flags like -o3, using dash line info, which is very important for your Insight Compute. And once you have got this binary, optimized binary, you use this command ncu dash dash set full that tells the NCU profiler that get all the metrics you can possibly find uh, from this binary and log them, and then you just run this binary, and during runtime it collects all these metrics. And when you open the application of Insight Compute, you'll be able to see a bunch of different metrics, but the two metrics that we care about are total number of cycles and total memory instruction count. You'll be able to find it somewhere. If you do some research about Insight Compute, you'll be able to see. And for this program that we are using, it's called 2mm.cu. It's from this famous polybench GPU open source code. It's basically a matrix multiplication of two matrices, and for this specific program the total cycle count was around 4.65 million, and I was able to recreate these exact numbers which are shown in the paper as well. So yeah, that is the total cycle count. And the memory instruction count, which is the global and shared memory load and store count added together, is around 100 million. And after we have uh, used the redsan tool and done the optimizations that it suggests, we'll come back and get another uh, benchmark, and we'll see if it actually was able to optimize our code. We look at how to actually install and run the redsan tool. These are the instructions from the paper itself. So you have to download the Docker image. The link is provided in the paper. Once you download it and extract the zip file, you load it into Docker with this command docker load, and then you run the image, giving it permission to access all the GPUs that your computer has. Your computer needs to have an NVIDIA GPU for this. And then you basically install the redsan tool with this command called source.bin/install release.sh. And once that is done, that will probably take like 10-15 minutes. Then you change your directory to this AE scripts, and then you have to do this important thing that inside the AE scripts there is a file called setup benchmarks. You have to modify it, and at the top of that file you'll see a flag called the architecture flag. that you have to modify to your computer's actual GPU hardware. For me, it was SM75, but depending on your GPU model, it might change. You have to do that, and then you have to run this command source setup benchmarks. This will basically compile all the benchmarks that this paper uses, like all the different programs, including the 2mm program from the Polyben GPU. Once that is done, you switch to that 2mm folder inside AE programs overhead, and you copy this example run.sh from this directory to the current directory that will be your 2mm folder. And after that, you have to open the example run.sh and edit the executable name at the end of that file. And yeah, it's pretty complex given the setup and everything you have to do. Another thing that you have to take care of is you have to do all of these instructions in the same shell, same terminal shell. If you change your shell in between, it might not work properly. That is one thing you have to remember. And once you do all of this and you run this last command, your output, the red sans output, will be generated, and it generates two files. It generates one file called as log files, and then it generates another file called as instruction account.csv. So from the log files, you basically get, for this 2mm uh, program, you have two kernels, two CUDA kernels inside it. In the log files, you get what base program counter is assigned to both the kernels. You need that base program counter. And inside the CSV file, it actually tells you every memory access instruction that was done through each program counter. And then it tells you if it's redundant or not. If it's redundant, the rate will be displayed. If it's 1 or anything greater than 0, then it's some level of redundancy is there. You look at each program counter which has a rate of greater than 0. That means there is something that we can optimize there. You take that program counter and subtract the base PC that you found through the log files for that kernel, and that gives you an offset. This is kind of like a hack. This is not giving you exactly everything you need. So once you get this offset, you have to open your NCU with the line info, the compiled NCU profile, and then you have to go through the source mapping and check this offset. So what I'm doing is, in this PPT you won't be able to understand everything, so I'm putting another video. I'll link that video in the description of this video, and there you'll see exact process and how to exactly see all these things. And basically it'll tell you the exact mm, program counters or the lines in your programs that are causing the memory redundancies. And once you get that, you can optimize it with multiple different techniques taught in this paper, like using the restrict keyword or using intermediate like register stores instead of having loop invariants, stuff like that. And when you actually do the changes to the 2mm program, you'll see the memory instruction count go from 100 million to around 67 million. And that's how this whole tool works and helps you. Obviously a lot can be improved with the software itself. uh, Currently the build system is not that easy for a normal everyday user. And also the calculation of offset and then going to the NCU and adding that offset, all of that, this takes some learning and is kind of complex. So those are some things that can be improved with this software, and I look forward to contributing to the repo and try to improve the build system eventually. So that's it, guys. That's about the paper, and you guys should see the video in the description. That will be like the full demo of how to actually run all these instructions and what output you see, and I'll also show you how you see the uh, all the metrics inside the tool, and that'll be more helpful for you to get an idea. And yeah, that's it. Thanks again for watching this video, and I hope you learned something about CUDA and GPU program optimizations. Thank you.